All right, so announcements. I will not have an in-person class Monday after break. Instead, you will watch a class video, and so we'll keep on pace. So I'll post all that on Canvas. So the video will be, it's one of my old videos from class just like this. They're usually 35 to 40 minutes. And then we'll just keep rolling with web work, and you'll have the written homework, do that Wednesday night when we get back. You also have that extra web work that's due Wednesday after we come back for the optimization stuff. So if you need assistance with that, I'll have the office hours Wednesday. I'll be back that Wednesday, but won't be here Monday, so no in-person class Monday. Instead, we'll have virtual class. Yeah?
Can we get bonus points if we watch the video in like a really cool place over break?
Share with us, where are you going?
I'm skiing, but like, what if we watch like on the top of a mountain or like do something weird like that?
Yeah, if you blog it, like if you make a YouTube of it, like so make a video of you watching the video somewhere cool.
So
I'll consider it.
If I'm doing it at work, then do I get bonus points?
That depends what your work is.
Dishwashing.
I mean,
Put my laptop in the dishwasher.
yeah, be creative, like. Okay. Questions about that? All right, so there's this one you're having a little more difficulty on this one that's due tonight at 5. And so this is basically, so we got a rectangular region. When you have a rectangular region like this, then you can easily just change the order of integration instantly. You can just say, do X first or Y first. But no matter what you do first in this one, when you get to the X, you're going to have to use one of these more advanced techniques from Calc 2. Anybody recognize what that is? So let's just get it over with. We'll do it first. Yeah, so if you had me, we called it undoing the product rule. If you didn't have me, it's called integration by parts. Integration by parts. So just getting you going here. It's the idea that f times g equals the integral of f prime g plus integral g prime f. Nope. Other way around. F g prime g f prime g. There we go. Okay, so this is the idea, and that our integral is like this, and we're trying to figure out what that antiderivative is. So with respect to x, so we got to set up what is the f and what is the g prime, or u and v prime, if you used u and v prime. So what are we going to set for f? It's going to be x or cosine? X, because what happens is then f prime is 1, and that just made everything 1 degree easier on your resulting integral here. That's the idea. So then you have the cosine here. So now we have a little antiderivative problem here. Antiderivative of cosine 4x plus y is sine 4x plus y. Is that it? Over 4, 1/4. And then, so then our answer is going to be fg minus, or u times v, if you did it that way, integral of f prime g dx. So when we're doing the inside integral, we're just considering like a single integral in terms of x. Y is a constant. So I'm using this single integral technique to do the first integral, which is the inner one, the inside. So that's going to be f times g is x over 4 times sine of that thing minus integral 1 times 1/4 sine. So, and this is all to figure out the part of the double integral that's with respect to x. So now this one is doable. 1/4 sine of 4x plus y is, you can just do that in the next step, and then that whole expression will be your antiderivative with respect to x, and then you'll plug in your x-intercept or your x limits and subtract, and then you'll have a straightforward integral with respect to y. to do from 0 to 1/4 pi. Okay, did that help? So, and if you do y first, you'll still, on the second time around, you'll still have to apply this technique when you get to the x eventually. Okay, hopefully that helps refresh your memory on that. Actually, I'll be around between 1 and 3 today. If you have any questions, I'll be in my office grading papers for another class. So if you want to stop by for web work help this afternoon, you can do that. All right, so I have a little animation to show you. So here's the beginning of it. This is the beginning. Okay, and then this is the second part. Starting over, here's the beginning. Part 2. So what does this, so you're finding a partner, everyone's discussing this. What's the context surrounding this? What does this have to do with what we're talking about in this class right now? There's lots to talk about. Go. Okay, so does this have to do with area? Does it have to do with area? Are we talking about area in this class? Nope. Not talking about area. Okay, this does not have to do with the area of the gray region. So what does it have to do with? Volume? Where's this is a two-dimensional figure. How is volume involved here? What's that? The base of it in? But the base of the solid in R3, right? So let me try to draw this here. Hey, I'm good, watch. You laugh. And? Yeah, is that the same thing? I don't have gray. You don't have faith in me. You see that that's the same thing? Okay, that's kind of like the same thing. So what are we talking about here? Someone tell us something else. I know Nick has lots to say. Anybody else? And that's a great thing. I love that. What do you think? Yeah, Matthew.
I'm thinking it looks like a type 1, like, because it's going, like, just in terms of how it's animated, it's going bottom to top, left to right.
What do the rest of you think?
Like,
It's illustrating a type 1 double integral? Yes, very good. Bottom to top, then? So bottom to top at any arbitrary x, right? So that I could have shown that here, I could have shown that over here, and then left to right. So once you like kind of accumulate across y values for a typical x, then you get like a whole line of think of rectangular columns, and then we're going to accumulate all those lines from left to right. Okay, somebody else. What else? Yeah, Sam.
In my mind, this looks like it'll just be one double integral.
Okay. It will only be one double integral because the bottom is the same single function for the whole bottom and the whole top. So that when you're looking at type 1 and trying to determine if it's broken up or not, it's about the bottom and the top. The whole bottom defined by one function and the whole top defined by one function, then we can do it as one double integral. But if either the bottom or the top is like split up into two different functions, that will force us to split it up and to add together double integrals. What else? There's a whole another thing we haven't talked about here. Yeah, Emily. Okay, to find what volume? So we really haven't established what volume we're talking about. Where is the volume coming from? Everything's two-dimensional so far. Where is this going to have to do with anything to do with volumes? You want to? Okay, when you say functions, are you talking about the red and the blue function? Do those form the volume? Yeah, Becca.
Do they just kind of like extend up and make like shape some sort of like solid figure?
Right. This is the region, and the region gives us the top, the bottom, or the sides. Sides. The region defines the sides because it's going to, like she said, we're going to extend that up and down, and that perimeter, that outline of that region is going to define the sides of this. So what defines the top and the bottom of this? What's that? What function? Yeah, so this is the context of this is we have some multivariable function, right? Z is a function of x and y. But I'm not showing here. This is just the region, right? This is just the region over which we're going to integrate this function. So in geometry, so I have some function f that lives, it's a surface, right? A surface in R3. And we only care about the points of that surface inside the region. Whatever this is. We only care about those points on the surface, the ones that are over or could be under, right? So the surface, in some places it might define the top, but then if the surface goes underneath the xy plane, it will be defining the bottom. And so if it's defining the top, then what defines the bottom? Yeah, right, xy plane, right? Z equals 0. So wherever the surface is defining the top, the xy plane, or z equals 0, defines the bottom, and wherever the surface is defining the bottom, then the xy plane defines the top in those parts. Okay, so your surface and your xy plane are, depending on where the surface is, are defining the top and bottom of this, and your region is defining the sides. Does this make sense? And so we're talking about a type 1 double integral, which means we're integrating over the region, this function. And the order of integration is? Bottom to top is dy to dx. dy dx. So the region defines the sides, like a cylinder. It's like extending it like a cylinder. Surface and the xy plane are defining top and bottom of this, depending on where the surface is. And then the value calculates. So when I calculate this value, I'm going to get area, volume. I'm going to get volume. I only get volume if what? It's all above. It's volume only if the function values are always positive, greater than 0, for the xy coordinates inside our region. So in general, it's not volume. It could be volume if your surface is always above the xy plane. So what is it always? What can we always say it is? Net volume, difference in volume, signed volume. And what's that? What does that mean? Net volume or signed volume. What is it? Yeah, Nick.
You have the volume above the
Uh-huh.
xy, above the xy plane. You subtract any of the volume from the below the xy plane.
Right. So any solids that are carved out above the xy plane have a positive contribution, and then any any solids that are carved out below the xy plane over that region have a negative contribution, so they get subtracted. That's what we mean by signed volume. Okay, does that make sense? So if this was rate of change, right, if it's rate of change, it's the same thing. It's just a rate of change function, like the snow on the mountain we talked about a couple days ago. If the function is positive, then, well, that would always be positive. But so if some rate of change that could be positive or negative, whenever it's positive, for those xy ordered pairs, your accumulation goes up. And wherever that rate of change function is negative, below the xy plane, that's pulling the accumulation down. Right? So that's like net accumulation, right? Net accumulation. Okay, so but what I've got here is truly a volume the way I drew it. It's truly the volume of this solid defined on the top by the function all the way down to the xy plane. So you got to imagine, you got this surface, you're going to take that volume all the way down to the xy plane. Okay, so that's what double integral does. So let's work on more double integrals. Any questions? So that animation is just for type 1. So a type 2 animation would be like this thing turned on its side, right? You'd have x as a function of y for left and right. You'd start left to right, and then you'd get a strip, and you'd accumulate all those strips from bottom to top. Okay, so let's work on these here. So here's a summary. Type 1, bottom function to top, left to right, dy dx. So here's type 2. So type 2 is going to start with dx or dy? Dx, which is left to right. So here's left to right. Did I do it? Left to right. There's a typical strip across, and then starting at the bottom, accumulating all the strips up to the top. All right, so here's some problems we're going to work on. Before we do that, let me get a strategy. So what we're going to do here is we're going to practice this by changing the order of integration. So we're going to figure out what exactly the region is that we have, and then we're going to switch it. If it's type 1, we'll switch it to type 2. And if it's type 2, we'll switch it to type 1. And here's a strategy for that. Here's a strategy. These are geometry problems. These are geometry problems. We're going to start by sketching the region based on the given limits. We're going to get a really good sketch. And then we're going to scrap the old limits and disregard them. I'm not going to look at them anymore in the original problem. We've got our sketch. We're going to just forget about the old limits, and then we're going to write the new limits of integration with the sketch. So it's all about the geometry. It's all about sketching the region correctly, understanding the region correctly, and then you're going to rewrite it it's like starting over with a new problem. Given a sketch, write it in the other order. Okay? And now getting these sketches correct. So if you have type 1, it's about carefully identifying the entire top and the entire bottom. That's going to be the key to a type 1. Whenever you're working in type 1. What's the entire top of it? What's the entire bottom of it? All right? And then, if it's type 2, you're focusing on what's the entire left side and what's the entire right side. In other words, the first. So that inside integral, or the first thing that you do, is the key to the kind of the boundaries of it. dy first, top to bottom. dx first, left to right. So those. So let's. We'll do this first one together, and then I'll let you loose on 2, 3, and 4. Questions on the strategy. This is about getting a really good picture and then using the picture. Not trying to look at the limits and figure out how to switch them. Because if they're functions like this, You can't just swap them like you can with a rectangular region. Okay, any questions about the strategy? All right, so here we go. Let's do the first one together. So this first one, is it type 1 or type 2? So that means, and is the bottom or the top split up, or is it one continuous function for the bottom and one continuous function for the top? Yeah, there's only one double integral, so that means the whole bottom must be something and the whole top must be something. What is the whole bottom? 3x. Now I'm not going to draw this to scale because 3x is pretty steep like this. It'll be harder to see, so I'm going to kind of draw like this, but this is 3x, okay? That's the whole bottom of it is that. And what's the top of this thing? 24. The whole top of it is 24. Let's see. Bottom blue. Top is, I don't have teal, but I got terracotta. Bottom blue, top terracotta. All right, and so from where now? So the outside integral is then from where are we starting the bottom and where are we starting and where are we stopping? So where are we going to start? From 0 to 8. And is 8 the intersection? It wouldn't have to be. So this top number here could be, could be anywhere in here. But I think it happens to be this point, 824. So it does happen to be that intersection, but it wouldn't have to be. Okay, so now I want to rewrite the order of integration. That means if we got the picture all right, we don't need this anymore. We don't want to get confused by that. So just scrap the old limits. And now we want to rewrite it as a type 2 based on the picture. So now type 2 means we focus on which boundaries? The left and the right. So I'm going to help you out with some colors here. So left, lemon. Awesome, I love it. Lemon. So where is the left side of this region? So it's 0. So this is the left. Does that show up on the screen? That's my left side. Okay, and so then what's my right side of this thing? Red. What? So what is the red or the right side? So it's the same as the bottom in this case, right? That bottom boundary of the triangle, it served as the bottom before, but now in the left to right context, it's the whole right side. So red for right. Okay, so here we go. So left is x. So we're doing what? Dx, dy. So left side is x equals 0. Right side is, the red one, would be x equals what? Y over 3. And that from? So where does that start? At y equals 0 and finally to 24. Questions? So again, we're kind of ignoring the whole context of R3 here. So this double integral is about some multivariable function that we're not showing in R3 that's hovering over this or underneath this region. And the double integral would find then the net volume of that function with regard to this region. So The limits of integration are all about the region in R2.
So the purpose of this is just to be able to interchange between type 1 and type 2?
Yeah, because so like there's different reasons what you want to do that. One of which is if it's sometimes you have certain like a rate function there that it doesn't have a standard antiderivative as type 1, but if you switch it to type 2, then you can actually get the antiderivative in terms of the other variable first. So that's one reason you'd want to do it. But another reason is these are great problems just really understand double integrals. You know, like when you practice these, then you just really start to get how they work when you do these switching. Okay, questions on this example? Okay, so go. So you have another one here. This one is given as what? Given as type 2 or type 1? It's given as type 2. So you're going to be focusing on left to right, the whole left side, the whole right side. Make the picture, scrap the old limits, write the new integral based on your picture. Okay, this one is given as a sum. But it's still just based on one region. It's still just based on one region. So you might be able to write it the other way with just one double integral. I don't know, or it might take two. But the point is that you don't have to, once you get that region, you don't have to keep it delineated the way this one is. You forget about the original problem, and you just have the one whole region, and then you decide, do I need to split it up, doing it the other way? Does that make sense?
Yeah.
So far,
Yeah.
Why is it 0 to 6? So, like, we think it's 6 months.
So 0 to radical x is like a typical strip this way, right? So you're saying where's the first typical strip on the left, and where's the last typical strip on the right? So the first one's here, and then where's the last one? There's the last one, 6. Make sense?
Yeah.
what's number 3? What are the upper bounds of that first?
You just can't read it?
Oh, is it 4?
4 and x plus 1.
Alright, I thought it was 4x plus 1.
Yeah, that one.
Oh, sorry.
But I got the negative 1 times x percent.
That helps you a little bit.
Yeah, that's what it is.
So I could like that now.
Are we good on 2? Can I erase and start 3? Keep working on 3. Keep. Okay, so are we switching to type 2 or type 1? We want type 2, and so we're going to focus on, with type 2, we need to identify which boundaries are the important ones.
Right and
Left and right, right? So left and right. The left and right are kind of the starting where we start. So left. What is the left boundary of this region? What is the left boundary? So I've kind of bolded the outline of the region here. What is the left side? Which function is the left side? Becca wants 2. What's that?
For part of it, the bottom's 2 part of it.
Yeah, so there's 2. So it has nothing to do with the bottom. So here's the region that I bolded. I want to know what the left side of that is. That's what I care about, the left side. There's 2 parts, right? And what am I using for left here? Lemon, right? Oh, sorry, did I mispronounce it? Okay. That's part of it, and that part, that is, right? There's the left side of this. Everyone see that? That's the left side. What's the right side? That's my red. So left is, here's the left. Is it 1 or 2 things? Just 1. The whole right side is just the one thing that's sloped. That's the right. Does everyone see it? That's the whole right. Okay, so now when we're doing this with type 2, what does x equals 4 have to do with this when we're doing type 2? X equals 4. Do we have to split it up about x equals 4? Do we have to consider that?
No.
It has nothing to do with a type 2 integral. So this is what students love to do. They want to go, oh, so now I got to go from the left side to 4, and then I got to go from 4 to the right side. Do I need to do that? 4 was what? Why was 4 important? Because it was
From our bottom to top.
which one, bottom or top? The 4 was the splitting point of the top. The 4 was the splitting point of the top. We don't care about that anymore. Don't care about this anymore. Doesn't play into the type 2 integral. So we're going to go all the way from the left, all the way to the right. And 4 is just somewhere along the way. It doesn't matter. X equals 4. Does it make sense? You don't have to keep this dividing line when you're doing type 2. So here we go. So we need to go from what's split up again? The left. Okay? That's going to be, and these integrals, the left is at the bottom of these integrals, right? So sometimes the left side is what? X equals 2. And sometimes the left side is y minus 1. Because this is y equals x plus 1. So x is y minus 1. So where is the left side 2? For what y values is the left side 2? From 0 to, is this 2, 3? Is this 0.3? So when y is from 0 to 3, that's when the left side is x equals 2. All right? And then when is the left side y minus 1?
From 3.
When y goes from 3 to 5. And then we said the right side is always the same. So these are going to, for the right side, these are my right side. And that's always going to be what? Negative 2y minus 7. Is that right? Oh yeah, you got to subtract 7 first. And then you're going to multiply by negative 2. So can we say negative 2 times y minus 7 like this? Does that work? Or negative 2y plus 14. It's fine. Did you catch it? Notice x equals 4 has nothing to do with this. You don't have to keep that. That was for splitting up the top. But we don't care about the top anymore. We got our left, we got our right, so we can just head all the way from left to right. Like 4 wasn't even there, right?
Real quick.
First question, yeah.
So when we're doing a left to right or bottom to top, whichever is first, whatever type 1 or type 2, both the first surface and the second surface have to just be one part, right? For it to be just not piecewise.
Both, yeah. So if you're doing type 2, both the left and the right would have to be one function to be able to do one double integral. If either side is broken up, so in this case, just the left side is broken up, that's enough to break it up.
How did you find the y value where the left boundary changes?
So that's just the intersection of x equals 2 and y equals x plus 1. Yeah, so you just get, it's just like finding the intersection point. So when x equals 2, then y equals 3.
Okay.
Does that make sense? It's the intersection of those two. Other questions? Do we have time? Did you follow this? That's a good example. If you follow and can do that one, you can do a lot. All right, quick, 4. Work on 4. I'll walk around for questions on this one. I'll leave it up.
So square root minus
Just dx.
oh yeah
That one half y.
yeah oh it would be 1/2.
You can't do one.
It is 1/2. So it's really like a line.
So, like in terms of solving, is that what you mean?
Yeah, like if it was like, so
It's gonna be like the top half like a circle. I'm just gonna square it. I'm doing that now.
Okay, we can get
When it's, oh, actually, I mean, I know the vague idea from it's
I
like,
don't think it works.
yeah, it's kind of,
Yeah, I see what you're saying.
this would be 5 like
circle orders with origins of 5.
it seems like
Divided the origins.
But by doing that, you're going to get some of y, and you're maybe that works. What do you think about that? Yeah, so that'd be the part. I mean, it'd be easy to check. Like, do it out like find the actual value of y and see if it's the same. And if you did that happen 3 or 4 times, then it's pretty common. That's right.
That's the X.
Questions about 3?
I'm not sure. So this is 2 root 5 is like where we stop and say like somewhere in the middle there. Oh, I bet that's actually the same thing. So it's root 5 over 2.
I think this one's
Okay, so that means.
Wow.
I guess we just I guess it doesn't have to be the intersection. Well, that's the y coordinate is like 5 fourths, but we don't think the x coordinate is. Oh wait.
So this x coordinate is 5 for the intersection.
It's like 5 fourths
Square root
times
still the right side.
root. Yeah, this is, yeah.
So the 1/2 y and the square root are, what are those? Left, right, bottom, top? What are those? That's left and that's right. So we said left is lemon. So there's my left. Sorry, I keep mispronouncing that. And then right. Okay. So that's my 1/2 y to what? X equals square root of 25 minus y squared, which is a circle, right? X squared plus y squared equals 25. Okay, now we switch it to type 2. Sorry, type 1. Type 1 means, what are we focusing on? Bottom to top. Bottom is this y equals radical, or 2 radical 5, the intersection? Yeah, it is. So this is the point, radical 5, 2 radical 5. Okay? And so bottom is 0. Y equals 0. What's the top? What is it? Depends. Depends on the x-coordinate. It changes. There's 2 parts to the top. Do you see it? That's terracotta. So that the top has 2 parts. If your x values are low, the top is the line. If your x values are high or close to 5, the top is the circle. So to write it as type 1, you got to split it up based on the fact that the top is split up. Bottom's always 0. So what's the top of the first part? Y equals 2x. Top of the second part? Y equals the circle written in terms of x. When is the top from 0 to 2x? When is the top from 0 to 2x? From 0 to? I think that's is that radical 5? I think 2 radical 5 is a y value. That's this y value is 2 radical 5. So I think this is that radical 5? So when x goes from 0 to radical 5, that's when the top is 2x. When when x goes from radical 5 to 5, that's when the top is the circle, square root of 25 over. So there it is. dy dx.